Okay, so welcome everyone, and thanks very much for joining us for the most recent Spatial ML seminar, and thanks again to Andrew Boutros for organising. So I'm very pleased to introduce our speaker for today. Our speaker is Lei Xun. Lei is currently a research fellow at the University of Southampton, where he specialises in efficient machine learning systems. He's affiliated with our centre, the International Centre for Spatial Computational Learning, a research initiative that's funded by the Engineering and Physical Sciences Research Council in the UK. Lei recently defended his PhD in electrical and electronic engineering at the University of Southampton. His research contributions have been recognised with publications in a variety of conferences and journals, including Transactions on CAD, DATE, CVPR, ECV workshop, and he won the Best Paper Award at Census AI Challenge IoT workshop. He's collaborated with researchers from the University of Oulu in Finland on the Finland 6G flagship research program, and also gained industry experience through research internships at Nokia Bell Labs and Huawei Cambridge Research Centre. Lei actively contributes to the research community by serving as a TPC member for CVPR, ECV workshop, ECCV, C4, CV4 Metaverse workshop, and also he contributes as a reviewer for a variety of different journals such as IEEE Intelligent Systems and IEEE Transactions on VLSI Systems. So Lei will be talking to us today about some of the work that he's doing at the University of Southampton, and I'm really pleased to have him here giving this talk. So over to you, Lei.
Okay, thanks, George, for the introduction, and thanks for everyone for joining us. It is my pleasure to be here and share our work. Today, I want to talk about how we build efficient machine learning systems using dynamic neural network and runtime resource management on heterogeneous computing platforms. All these works are done in collaboration with my supervisors, Professor Jonathan Hare and Professor Jeff Merritt. So let's start. Deep neural network inference is increasingly being executed on local devices because there are advantages in low latency and improved privacy. However, these models are both computational intensive as well as memory access intensive. So it is very important that we apply model compression techniques to efficiently deploy these models on local devices. There are many model compression techniques in the literature, but the most common two are pruning and quantization. Pruning is the techniques to reduce the number of model weights, and quantization is the technique to reduce the size of each model weight. However, although these methods are effective, it is important that when we deploy the model, we apply these techniques in a platform-aware fashion. Here is one example from the previous literature on platform-aware model compression. The idea is basically to find out how much pruning we need in order to meet the performance target while keeping the accuracy as high as possible. The key idea that is that we compress the model to adjust right size so it can meet the application performance target. This work, net adapter, has three components. First, the net adapter system receives a pre-trained network backbone as the input, as well as user-defined performance budget. Secondly, the system also receives empirical measurement from real hardware, and this budget and measurement could be the latency, the energy, and the power of the system. And the final step is to apply filter pruning to the model. So basically, we apply the pruning while measuring the performance on real hardware and compare the measurement with the target, and basically stop the pruning process as soon as we meet this target. So that's when we can keep the accuracy as high as possible. Now just give you a little bit of visual about this idea. So here is a typical accuracy versus latency trade-off curve from a model compression idea. And for a given latency target, we can apply this platform-aware model compression to find the most accurate model under this latency target. Right? Very often, if the latency target is very tight, then we have to trade off accuracy to achieve that tight latency requirement. And the target here could be other things as well, such as the energy consumption or the power consumption. However, the question is that could the hardware availability change at the runtime? Because this platform-aware model compression is based on that the hardware is a fixed resource and the target is also fixed. But at the runtime, we might have dynamically changing hardware resources, and the performance target could also change at the runtime. So let me explain this. So modern heterogeneous platforms are dynamic. They are equipped with heterogeneous computing resources, such as CPUs, could be different types of CPUs, GPUs, MPUs, DSP, and FPGA. Their availability and performance could vary dramatically at the runtime. This could be influenced by factors such as the device state, the power constraint, and the thermal constraint. Moreover, at the runtime, the deep neural network models might need to share hardware resources with other applications or models. All these runtime scenarios are typically unknown at design time, which makes the previously mentioned static model compression techniques less effective, because now we have a moving trade-off curve. Now let me give you some examples. So here we did some measurement by deploying a model on both CPU and GPU of the NVIDIA Jetson Xavier NX platform. And as you can see on this figure, bar A and bar E, they are statically compressed model using methods such as net adapter. And we compress the model to just meet the required latency target. You can see that it's just below the target line, so that we can keep accuracy as high as possible, right? But at the runtime, if we look at scenario B, C, D, and F, G, H, when the clock frequency drop due to thermal issue, so basically when the hardware is also shared with other applications, we can see that the original target can no longer be met. Another scenario is dynamic application performance requirement, which could also change at the runtime. So the idea is that the same DNN model can be used in a variety of different applications. For example, we could have some translation model as the backbone for different applications. But obviously, these applications have different performance requirements. For example, text-to-text translation might not require very high, very low latency, but require high accuracy. On the other hand, speech translation is real-time, require low latency, but the accuracy might be more tolerant. So in general, we talk about two dynamic scenario, dynamic hardware runtime condition and dynamic application requirement. The first one will lead to a moving trade-off curve, and the second one will lead to moving performance target. So in order to address these two kind of moving target and dynamically changing hardware, we need a dynamic neural networks to do dynamic compression. Before I introduce my work, I want to give you a quick overview about dynamic neural networks. Generally speaking, the dynamic models have a few formats. It could be width scaling, basically changing the number of channels or kernels at the runtime. It could also be depth scaling, basically changing the number of layers at the runtime. The key idea is to enable the partial execution within a network. So at the runtime, we can trade off between different performance matrices, such as accuracy and latency. Dynamic model could also be bit width scaling. This is basically dynamic quantization. And in my talk, I will not talk about this type of work, but if you are interested, you can look at the cited paper, as well as these two very good review papers on dynamic models. The one common question is that how we can build dynamic neural networks, because by default, neural networks are static, meaning every time we want to execute a model, all the parameters need to be used. Otherwise, we get random output results, right? So however, for dynamic model, these support partial execution to trade off between different performance matrices. And the key idea behind many dynamic model are novel training algorithm, which I will talk about a few in the next slides. So the first idea I want to talk about is incremental training. So the first method, this is one of the earliest dynamic model. In this work, the network is trained incrementally, one portion at a time. So as shown in the figure, you can see that when they train the model, they first train portion A, and then they train portion B while using the pre-trained weight from A. And finally, they train portion C while using pre-trained weight from both A and B. After all the training is done, you now have three subnetwork configurations. They are A, AB, and ABC. And in that case, they have different accuracy, latency, and energy power consumption. So one issue with this method is that although they have these dynamically scaling convolution layers, they are sharing the last fully connected layers. This leads to later training can actually affect the performance of previous trained subnetworks. To solve this previously mentioned issue, later works such as Slimmable neural network proposed using multi-objective training. It uses a sandwich training method, which basically at each training step, they pick the largest model, which is the full network, as well as the smallest subnetworks and some random subnetwork configurations in between. So that is why it is called a sandwich rule. And they do this multi-object training so that all the subnetworks can be improved together rather than later training kind of cover and affect the previous training. And the final work I want to talk about is mutual net, which is very similar to Slimmable neural networks. However, it also added input resolution scaling to the channel scaling space. So basically, this idea is kind of like compound scaling from efficient net. Basically, when you have a large input image, you tend to need a bigger model with more layers and channels. So they also added this scaling to find additional trade-off opportunities. Okay, so this was a quick overview and some background information about the dynamic models. Now I want to move to talk about our research. So in general, we identified three common issues in all previous dynamic neural networks. First of all, they all have a significant training cost. Secondly, the conflict with state-of-the-art neural architecture search method. And lastly, they are very inefficient on heterogeneous computing platforms. So let me explain them one by one. So what do I mean by training cost? So if we look at a typical kind of model deployment pipeline, we start with a pre-trained model, right? Then we apply platform-aware model compression to get an efficient model for deployment. But where does the dynamic model training comes into this pipeline? Ideally, we want the dynamic training to be done after the efficient model, because if we apply the dynamic model training to the original model, then some subnetworks are never used because they are just too large for the platform. But we still needed to keep this weight in the dynamic model. So the training cost involved in this pipeline, first we need to train the model, right? Then we needed to apply model compression to a platform and fine-tune the model to recover accuracy. And then finally, we need to retrain the whole model from scratch again, using completely different dynamic neural network training method. Fundamentally, the dynamic model training method is try to get subnetworks from static backbone. But the question is, in a modern era of a neural network, do we still need to do that to get subnetworks? The answer is no. So let's have a look. This network, this is a once-for-all network. It is a super network that was trained once and to get 10 to the power of 19 subnetworks. These networks are pretty flexible. They can change in 4 dimensions: width, depth, kernel size, and input resolution. And this method is very general. Although the original paper was applied to image classification, it was later applied to different application domains such as NLP, GAN, and the 3D models. The issues with this model is that because the large space, we cannot do the model search at the runtime for quick switching because it's not feasible. And also, the original search algorithm is designed for searching one static model for static kind of requirement. But for dynamic model, we need a better search method, because in dynamic neural networks, we need a library of models, and they have different performance trade-off between these models. And now let me explain why the kind of previous dynamic DNN training is conflict to the OFA model. Because if we apply the training to the output static model of OFA, then we basically reverse the benefit of OFA, right? So remember the idea of OFA is train the model once and get a subnetwork to be deployed directly. But if we apply the previous dynamic model to the OFA, then we reverse that benefit. And lastly, I want to talk about this inference inefficiency on heterogeneous hardware. First of all, when the hardware is sharing at the runtime, ideally we want to move the task between heterogeneous resources such as CPU, GPU, NPU, DSP, and FPGA. However, based on the previous research, you can see that on a heterogeneous platform, different computing elements prefer different hardware architecture. For example, the GPU prefers shallow and wide architecture. CPU prefer deep and narrow DNN architecture. So basically, these two are opposite to each other, which means the flexibility we need on a heterogeneous platform are not covered yet by the previous method, which using mostly either width scaling or depth scaling. So what we are proposing here is we try to combine the benefit of dynamic model, which we have a small amount of subnetworks to support faster switching to do performance trade-off, but we will also want to the kind of the flexibility, the quality of the subnetworks from the once-for-all network. And here, basically, what we are proposing is I think we need a mental shift about how we build the dynamic models, right? Because previously, it's all about how we generate subnetworks, right? But nowadays, since the super networks, such as once-for-all network, they already have a large amount of subnetworks. The question becomes how we can sample these subnetworks for heterogeneous platforms. So what we are proposing is that we need to find a small number of best architecture, and we're using that to build the dynamic model. This is the idea of Dynamic-OFA. So here is the block diagram of our Dynamic-OFA. So it uses OFA network as a backbone, and at design time, we do a lot of sampling, and we take the models on the parietal front to form a dynamic model. And two things I want to address here. So because the search space is too large and we want to have a library of subnetworks with different trade-off, so we change the search space from global space to local space. We initially search the biggest model, and we slowly shift the search window by changing the network size range. And secondly, we do the search for CPU and the GPU separately, because as I mentioned before, they prefer very different architecture. The benefit of using this OFA as the backbone is it contains all the efficient model for all kinds of hardware component. What we need to do is to build libraries for each hardware component. And these libraries are essentially masks. So during inference, we apply mask to the backbone model based on the hardware we want to run and based on the performance target we have. And here is a comparison, the accuracy and the latency trade-off between our work and the previous works. First, I want to point out that we are still a little bit lower than the static OFA backbone. This is because they treat each network as individual models. These are three models with three set of weight, and they fine-tune the weight to boost the accuracy a little bit. In our case, we have one model and many subnetworks. In this case, we have 7 subnetworks on CPU and 6 subnetworks on GPU, and they all sharing one model weight, which is the weight of the largest model. And compared to other dynamic methods, you can see that our method is more efficient. One thing I also want to address here is the difference between a dynamic version and a static version. This is a very common trade-off in the literature. So for a dynamic model, it is usually a little bit, in terms of accuracy, it's usually a little bit lower than its static version. For ImageNet top-line accuracy, I see that most commonly the dynamic version is 0.5 to 1% lower than the static version. And finally, I want to address this again. So basically, previous method of focusing on how to train static model to generate the subnetworks, either through channel scaling or layer scaling. But in our case, we're focusing on sampling from super networks and get these efficient subnetworks to building dynamic models, which is much quicker. And here I want to talk about a few runtime scenario. So first, we have a moving performance target. The x-axis here is the real time. The y-axis here is the latency target. So in this experiment, we basically deploy the Dynamic-OFA on the system, and we're changing the performance target and design runtime to adjust the model to meet that target. And you can see that from these blue lines to this red line, these are indication that once we have more resources or more relaxed target, we can always recover the model accuracy. The next scenario is we deploy Dynamic-OFA model to share the GPU resources with another application. So you can see here the x-axis is also real time. So about 2.5 seconds, we start another application, which is a plant classification, also a neural network model. And you can see that this breakdown is caused because the other model use a large chunk of GPU resources. So our Dynamic-OFA model suddenly becomes slower, and the runtime manager will adjust the model to smaller configurations so it can still meet the 60 millisecond target. And the last, scenario is two Dynamic-OFAs sharing the same GPU. So in the previous case, we have one dynamic model share the resources with one static model, right? So we can only change the dynamic model to do the trade-off. But in this case, because we have two dynamic models, we can design runtime to let them give resources to each other, right? So they can both coexist and trade off a little bit on themselves and meet their performance target. And now I want to shift the topic a little bit, because previously we have discussed our method on the dynamic model, which is at the application layer. But in our system, we see the system as 3 layers. We have a device layer, which are all kinds of heterogeneous computing resources. Application layer could be other applications, could be static neural networks, and it could be dynamic neural networks. And it could also be multiple neural networks or workload. And we have a runtime resource management layer, which will monitor the performance and the constraints from both application and device, and try to tune the knobs for hardware and algorithm as well. In the case of dynamic neural networks, the tunable knobs could be the model configuration, right? For the hardware, we can change the clock frequency and voltage, and we can do task mapping to choose different heterogeneous cores. We think it is necessary to explore the opportunity from both hardware and the software at the runtime, right, to address this computation issue. So let me explain why we need a software and hardware co-design approach at the runtime. So first, let's think about a scenario about that, for example, we are algorithm developer. We only develop algorithm. We know nothing about the hardware. So in that case, let's say we have a dynamic model with 4 different configurations. So the 25% model only using 25%. So we divided this model into 4 groups of weight. The 25% of model only using 1 group of weight, and the full model using all 4 group of weight. And from a algorithm developer perspective, the trade-off we can see here is this is the energy versus latency trade-off. We can see 4 points representing 4 different model configurations. So these 4 models have different energy versus latency trade-off, right? But if we are pure hardware developer, we know nothing about the algorithm. Now what we can do is dynamic voltage and frequency scaling, as well as task mapping. And in that case, so these 2 lines, this is the trade-off curve of A15 CPU. This is the trade-off curve of A7 CPU, and different point here meaning different clock frequency levels. So that's all the trade-off point we can get. It is more than pure dynamic model method, but the benefit we're proposing is we combine dynamic model with DVFS with task mapping. So you can see that now we have a much larger trade-off space with wider trade-off range and much fine-grained trade-off point. So that basically gives us more options to do the trade-off at the runtime. So in conclusion, we think that optimizing DNN models at only design time is not sufficient because the hardware might change at the runtime. The performance target might also change at the runtime, right? So we need to think about this, what could happen at the runtime, right? And we think a dynamic model is important in this system design because it can provide more trade-off point to the existing hardware opportunities, right? And in our design, we consider tuning both software and hardware runtime to meet dynamically changing resources as well as the kind of targets. And before we move to question, I want to quickly say that we are also open to new collaborations with our partners. At this three-layer system diagram, we think that there could be more opportunities on hardware. So at the moment, we have tried dynamic models on CPU and GPU, but we are thinking it could be more opportunity that we run these models on NPU or reconfigurable hardware or processing memory hardware, right? And also, can we design more dynamic models with different applications, such as transformer, GAN, and 3D models? And also, as I mentioned, with more heterogeneous hardware, right, we do need to redesign the dynamic model to supporting this heterogeneity. And lastly, we're also very interested in, can we design runtime manager for managing multiple dynamic neural networks? Because managing the hardware, the clock frequency, the task mapping, the space is already very large. By multiply this with the software, the kind of trade-off opportunities, then the searching space basically exploded. So how can we design efficient runtime manager? It's also a very interesting question to us. So I think this is the end of my talk. You can connect with me on LinkedIn. You can find my previous talks on my YouTube channel, and you can find the related paper here as well as on my Google Scholar. So thanks everyone for attending this seminar. I'm now open to questions.